Good afternoon. And so I want to continue to talk about planets. But instead of talking about detecting planets, I want to talk about how planets form. This is actually a very similar slide that's shown in the previous talk, where each of these dots represents planets that we know about. And the little circles represents the planets that are orbiting around the stars. And you actually also see our own solar system. And you can see what's interesting about all these planets that we are forming is that most of their architecture, the orbital radii of the planets, are much different from our own solar system, which makes it very interesting. There's probably other planets, there are probably other planets that are further out that are very much like our own solar system, but those are much harder to detect. So one of the interesting things is why are all these different planets, all these other solar systems we detected so far, why are they so much different from our own solar system? And to really understand that, we have to understand how planets form in the first place. And so one of the telescopes here in Chile, ALMA, is one of the best telescopes in the world to try to understand how planets form. And so we have a basic model with how we think stars and planets form. And this is the basic picture that we want to test. In interstellar space, there's very large clouds. There's thousands and billions of kilometers in size, containing mostly molecular hydrogen. Those are actually the smaller clouds. Some of the clouds can be hundreds of times larger than that. But for reasons under the force of gravity, these clouds will start collapsing to form a star. And so you go from hundreds and billions of kilometers just to maybe a few thousand kilometers in size to form actually a star. But as that star forms, you get a rotating disk around it of gas and dust. And this rotating disk is where planets form out of. This is how our own solar system, the planets in our own solar system, formed 4.5 billion years ago. And right now, there are stars forming. They're roughly 1 million years old, and they are right now containing these rotating disks of gas and dust. And that is where that's where the planets are forming. This is not a new idea. This is something that's been around. The German philosopher Immanuel Kant proposed this idea a couple centuries ago. And that basic model is still what we think is valid today. Here's a more modern picture of that, how the picture of a planet forms. This basically represents the gas and dust around a star, and you have a planet that's forming out. And as that planet orbits around the star, it actually accumulates all the material around it. And so the planet grows and more massive as it accumulates material around the star. And as it becomes more and more massive, it actually starts carving out these gaps within the disk, because it's so much mass and so much gravity, it could actually clear out a section of the disk. This is the end result after a couple of million years, where the planet itself is located right here within this blue circle, and this black material around here basically represents a gap that's formed around the disk. This is basically the gap the planet has carved out as it orbits around and around the star. And you also see these spiral patterns that are around the star. This is just due to the gravitational interaction of this planet with the gas and dust surrounding the star. It creates this spiral pattern. And so this, ideally, is what we detect. Can we actually detect the signature of planet formation in these disks around these very young stars? And this is where ALMA comes in. So ALMA is a new telescope. It's only been operational about 6 or 7 years. It's located in northern Chile, and it's the most powerful telescope in the world of its kind. Much more powerful, many more times more powerful than other similar telescopes in the world. And what ALMA can do is detect the gas and dust within these disks. And the dust within these disks, there may be on the order of millimeters in size. It's like a grains of sand, but they're distributed all throughout. But ALMA, even though they're many, very far away, these disks and these stars, ALMA can actually detect these small grains of dust within these disks. And it actually also detect the gas as well. And so this is one of the main reasons why ALMA was built. And a few years ago, we were testing out some of the new capabilities of ALMA, and we pointed to a very young star. And you probably have all seen this. This is the image of a star we call HL Tau. And in the upper right shows the image of the dust that ALMA produced around the star. And you see this nest of rings, dark rings around the star, many, maybe on the order of a dozen rings or so. And when astronomers saw this, there's two things that came to mind. One is, are each of these rings, is that due to a planet? And that would be a very remarkable result, because this is exactly what you'd expect from the model that I showed earlier. But there's something very puzzling about this. This star is less than 1 million years old, and all our models suggest that planets have to be, the time scale to form planets has to be much longer than 1 million years. So it's very much a puzzle of why you could see planets, so many planets presumably, around this young star. But astronomers are very clever, and so they thought perhaps these rings aren't planets after all. Perhaps this is actually due to something else. And one of the possibilities, there's many possibilities, but one of them thought is maybe it's not a change, maybe it's not due to a planet, it's actually just due to a change in the dust properties. Because maybe the composition of the dust or the size of the dust changes as a function of position within this disk. And if that happens, then the amount of emission, the amount of dust emission you see will change as a function of radius. And so that's what that's one possibility. There's other possibilities as well of how you can form these rings. And I wish I could tell you the answer, but we don't know the answer of what causes these rings. There's many different people have different ideas, and they support different models. So one of the exciting research topics with ALMA is trying to understand what is actually the origin of these dark rings. Is it due to planets, or is it due to something else? And so this is why the dust particles, the dust composition may be very important in understanding the properties of these rings. When the dust is very, very far out from the star, the dust is very cold, and it gets formed, and then ice surrounds the dust particles. And so you basically have the dust is composed of silicon and carbon, magnesium, and other heavy elements surrounded by these ice mantles. But as you get very close to the star, the ice starts to melt, or actually sublimates into gas. And so in the outer part, you have these ice-coated grains. In the inner part of the disk, you have basically you have the bare silicates and carbon grains. And those different properties will tell you the amount of dust emission that you see will vary depending on how much these ice mantles that you have. And so that is the thought that each of these dark rings represents where you have different amount of ice evaporating from these dust grains. So how can you tell the difference between these? And that's actually hard to tell the difference between these different models. So what astronomers do when they don't understand, they just observe more disks and try to understand what are the different structures that one sees. So here's a gallery now of additional disks that are observed with ALMA. We're on the order of about a dozen, or about half a dozen to 10 or so that have been imaged at the same scales as the HL tau disk. And so these are some of the images that have been produced within the past year or so. And so the immediate thing that you see is that some of the structures that we see now within these disks, they're much different from HL tau. You do see some rings, but they're maybe not be as numerous as you see in other disks. And you also see some spiral patterns, especially in this star called Elias 27. You see this beautiful two-arm spiral that you see within this disk. And this is also very similar to the model that I showed earlier. We see the spiral pattern. So we have a very strong inclination that the spiral pattern is actually due to a planet formation. But you also have these other different ring-shaped structures which we don't fully understand, and that's what we're trying to do. So there's other clues that we actually can also make, and that is, in addition to studying the dust, there's also gas within these disks. Most of the gas is in molecular hydrogen, but there's also other molecules like carbon monoxide, formaldehyde, and all these different molecules. And we can actually map out the distribution of these molecules within these disks using ALMA. And from that, can actually understand what is the composition of the gas, and actually will tell us not only the composition of the planets that actually ultimately form. We can also see how the gas composition changes with the function of position with the disk. Does it change within these gaps within these disks? All these things are all different clues to understanding what is the origin of these gaps and origin of planets within these disks. And so here's this is actually these are 4 different images of the same disk. One image in the dust, and the other 4 images are in the molecules. These are all, so you see if you look in the disk, look at the disk in the dust or in the gas, you see different structures. And this all represents the different chemical composition within the disk and how you can trace it. So this is a very important thing for ALMA, what ALMA is doing right now. And another thing that we're going to look at pretty soon, this year, we have a new detector that's being installed at ALMA. And starting in March, we'll be able to start mapping out water within these disks. So there's water vapor within these disks, which is very critical for understanding the formation of life within these planets, because eventually this water vapor will be forming in the atmospheres of these planets and potentially on the liquid oceans on some of these planets. So later this year, we'll be able to mapping out the warm water vapor that is associated within these disks, XENs. So this would be also a very important clue to understanding these rings. Can we see changes in the amount of water vapor when we see these rings, dark rings, and when we don't see them? So what's the ultimate goal of what we would like to do with this? And so if you try to forecast out 10 years from now, what would we really like to see, what would be really definitive proof? Can we actually see a planet that is forming actually located within one of these gaps? You can't detect the planet itself with ALMA, but what you can do is use other telescopes, many here including here in Chile, to actually detect the planet itself at optical and especially infrared wavelengths. And so there's the VLT, which is another telescope here at Paranal Observatory in northern Chile, is one of the best telescopes in the world at trying to do this. But even then, that telescope is like 8 meters in diameter, and that may not be large enough. And so they're building another telescope in Chile, which would be 39 meters in diameter, and that may have enough power to actually detect the planet within the gaps within these disks. There's also a space telescope that's being launched next year, the James Webb Space Telescope, the JWST. That also may have the potential to detect the planets within these disks. So if I look out over the next 10 years of what you'd expect to see, we're going to be a lot of effort trying to detect the planets within these disks, within these gaps within these disks. And if that occurs, that would be a very powerful moment, because that would really confirm that we're actually seeing the formation of planets actually occurring within these disks. So with that, thank you.